Hello, I'm Tim Lichtenberg from Oxford, and here I present the results of our research published in Lichtenberg and Kreit 2021 in AppJ Letters. Our work concerns the combined evolution of the chemistry and dynamics in the disk and geophysical processing on planetesimals may alter the abundance of carbon during planet formation. Carbon compounds are essential for habitable worlds. Curiously, however, carbon is strongly depleted relative to the nominal values in the Sun or in the interstellar medium. The left plot here shows the amount of carbon relative to silicon and various extraterrestrial materials in planetary bodies relative to the Earth, which is depleted by several orders of magnitude. This can be compared to water, as seen on the right. While the global oceans make our own Earth seem to appear like a water-rich planet, it is in fact very dry. The same is true for carbon. While it is crucial for climate and the basic chemical ingredients for life, too much of it would be destructive rather than positive. The strong carbon depletion can also be seen in meteorites, here shown as carbon mass fraction versus the C/N ratio in meteoritic materials. Carbon is most depleted in the Earth relative to all other meteoritic objects. This seems to suggest that carbon is depleted somehow during planet formation. But where does this trend start? At the beginning of planet formation in the interstellar medium, we find roughly one carbon, oxygen, and nitrogen atom for every 10,000 hydrogen atoms. In cold molecular clouds, these elements are distributed among different carriers. For example, roughly half of the carbon is in refractory compounds, which have high condensation temperatures, while a significant fraction of carbon, and also oxygen, is in carbon monoxide. If we imagine these raw materials are incorporated unaltered into a protoplanetary disk, we can compare the condensation behavior to the temperature and pressure found in different locations to predict what the composition of the solids, or ices, and gas there will be. For example, if you imagine starting here close to the star and slowly moving out along the midplane, the decreasing pressure and temperature would result in water, carbon dioxide, or carbon monoxide to disappear from the gas and form ice, resulting in this step-like behavior for the C/O ratio. This picture is very powerful in simplicity, but it assumes the disk to be static and that these molecular ratios are fixed. A hint that these assumptions may break down comes from the warm molecular layer. Here above the disk midplane, the temperature never drops to very low values. The decreased pressure results in many of the volatile molecules never being stable as ice. In this layer then, you would always expect to see the CO to H2 ratio of about 10 to the minus 4, as inherited from the ISM. However, there's mounting evidence that this is in fact not what happens in nearby disks. This plot here shows how the gas phase CO abundance in the warm molecular layer decreases by almost 2 orders of magnitude in about 3 million years. The data points are in some cases individual disks, and in other cases entire star-forming regions. Understanding the causes of this depletion is crucial because these timescales are similar to planet formation timescales. CO represents a large reservoir of carbon and oxygen, but also CO emission is often used as a tracer for total disk gas mass, a calculation that requires knowledge of the CO to H2 conversion factor. Last year, Sebastian Kreit and colleagues attempted to explain the CO depletion through numerical models. They found that a combination of ongoing chemical processing in the midplane and sequestration of CO ice on pebble-sized particles, which are effectively confined to the midplane dynamically, could deplete the surface regions by the observed 2 orders of magnitude on the relevant timescales. Crucially though, both processes contributing to the CO depletion require mixing between the surface layers and the disk midplane. Through this connection, the observed gas phase abundance in the surface layers allows to constrain the composition of the ices in the disk midplane. In the modern picture of planet formation, pebbles accumulate in certain disk regions to form dense clumps that collapse to form gravitationally bound planetesimals. The bulk composition of the primordial planetesimals is then set by the composition of the pebbles. For our new study here, we looked at the pebble compositions predicted by these disk models, which vary significantly with both time and location, and asked what would happen to planetesimals born with such compositions. In the solar system at least, early formed planetesimal bodies did not remain in their pristine state because radiogenic internal heating from aluminum-26 substantially heated and thermally processed planetary bodies. This heating is short-lived due to the 700,000 year half-life of aluminum-26, but it can be extreme. On the right, you see an illustration of the strong magmatic activity that can develop on early formed bodies. Here, we see a video of a 3D simulation of a spherically symmetric, silicate-dominated planetesimal that melts and internally deforms due to the strong radiogenic heating. This can have strong consequences for both the structure and volatile abundances of these bodies. The bottom part on the left illustrates how iron cores on planetesimals form due to radiogenic heating, and upper parts shows how initially volatile ice-rich planetesimals melt and degas their primitive volatile abundances that are inherited from the disk. Evidence from meteoritics suggests that this devolatilization process after planetesimal formation substantially shaped volatile abundances of the meteorites we measure today, and the final bulk volatile abundances of the forming terrestrial planets. However, the initial abundances of aluminum-26 can vary by orders of magnitude across planetary systems. This means extrasolar planetesimals can be heated to similar levels as solar system objects, or not at all. This may have profound influences on the volatile abundances of planetesimals formed in carbon-rich regions of the disk, as suggested by the rapid variation with time of CO abundances in ALMA disks. In our project, we therefore explored how the evolution of the material composition in the disk plus the processing on planetesimals evolves with time and for different initial conditions of the planet-forming system. On the left, you see the starting conditions of the disk system. The volatile to rock ratio varies radially. We focus on the region that can be probed with current disk observations, which is dominated by the evolution of the CO content. The next step in our model is the time evolution of the disk, where the composition of the dust grains evolves due to dust coagulation, settling, radial drift, and chemistry. At some point, planetesimals are formed, which is a free parameter in our model. In this case, it is at 2 MegaYear after planetary system formation. At this time, the composition of the dust is inherited by the planetesimal, whose composition then evolves according to the loss rates predicted from planetesimal degassing, which is a function of the planetesimal size and the heating rate from radioactive decay. On the bottom right, you see a parameter map of the heating of planetesimals as a function of this enrichment level of the planetary system, from a solar-like enrichment level to 1 magnitude below. Possible volatile loss in planetesimals is compared to the maximum temperatures reached. According to degassing experiments on chondritic meteorites, CO, H2O, and CO2 feature different outgassing temperatures, where CO2 is lost first, followed by H2O, and then CO. In the bottom left, nearly all is retained. In the top right, nearly all is lost, but the time of loss can vary strongly depending on heating rate. The combined evolution, shown in the bottom left, illustrates that across the disk, the abundances in all volatiles sharply decrease, but at different levels that, generally, are a function of the heliocentric distance, timing of planetesimal formation, and internal processing. On the next plot, we compare different heating rates, which are displayed by different shadings, and different cosmic ionization rates of the disk, which drive disk chemistry. The black cases show the final CO content for planetesimals forming at time 0 of the disk, effectively negating disk processes like chemical processing and radial transport of pebbles. The yellow cases show when planetesimals are formed at 3 MegaYear instead, when such processes are given time to occur. This demonstrates that, first, the CO content of planetesimals is a strong function of the internal degassing rate, and second, that for varying formation times, distinct peaks can develop that display the radial variation due to disk chemistry. The disk model itself, meaning the disk size, mass, temperature, and other physical parameters, remain identical, and all the variation seen in the plot comes from variations in degrees of disk processes and assumptions about the planetesimal formation process. Importantly, these results are in contrast to the situation described during the introduction, where the snowline location alone was responsible for the composition of solids and ices available for planet formation. This adds timing as a first-order parameter important for planet composition. These predictions therefore offer a way to test the level of geophysical processing of planetary building blocks on a system-wide level. Before speculating about planets, we note that observations of the second-generation gas and debris disks offer potentially a way to derive bulk CO and CO2 content of planetesimals in such systems. Hence, the abundances in debris disks may give insights into the volatile chemistry that is set by disk and planetesimal evolution and can be compared to pristine solar system objects that could escape thermal processing. Our simulations in this context suggest variations between planetary systems that should scale with the formation time of planetary bodies. Earlier formation of planetesimals means more processing, which means lower volatile abundances. If only a fraction of systems reach this efficient planetesimal processing stage, this means that statistically the variance in carbon abundance across planetary systems should increase. Some systems may show very low abundances, while the not processed systems should resemble the chemistry set during the protoplanetary disk phase. We suggest that carbon abundance of planetary systems are globally influenced by disk chemistry and the geophysical evolution of planetary bodies after planetesimal formation. The inherited composition from the disk is set by gas and grain surface chemistry, pebble coagulation, and dynamics in the disk. Once planetesimals are formed, however, the local dust composition is altered by internal evolution due to heating from the interior of the body. Evidence from the solar system suggests that this heating is strongly time-dependent because of the short half-life of the most important radionuclide for heating, aluminum-26. The resulting degassing and devolatilization of planetesimals then crucially influences the volatile content that can be delivered to terrestrial worlds during the primary accretion phase, and potentially during later accretion episodes due to dynamical mixing processes. The volatile precursor material that makes up the atmospheres and oceans of terrestrial planets in the inner disk in this scenario is a combination of the time evolution of disk chemistry and geophysical reset in growing planets. This presents an alternative to the standard scenario that is typically considered. Volatile and specifically carbon abundances are crucially influenced by the timing of planet formation. Thank you very much for your time and attention.